This lesson will cover applications of exponents. The learning goal is to solve problems that involve exponential functions, and your success criteria is you can solve an exponential growth or decay problem given the situation, and you can determine the exponential equation for a given problem and solve it algebraically. So an exponent is used to indicate repeated multiplication or division, and thus rapid growth or decay. Now, there are many example things in the real world that grow or decay exponentially, and there are many who believe that exponential function is one of the most important functions because of its application to our daily life, and its importance to modeling economic, environmental, medical, and other phenomena. There's an additional video here which you can watch that gives more examples of how an exponential function is applicable to our daily lives. So, for example, a lot of things that the exponential function can model is infectious disease. It can model climate change, and even population. If you think about it this way, if you have one person who has two children, each of them have two children, and each of them have two children, we can see the growth from one person to two people to 4 to 8, and then you can see the pattern already 16, 32, 64, and so on and so forth. Exponential growth is, well, it's exponential. It gets very large, very quick, very fast. So what does exponential, what does an exponential function look like? So we have what's called the growth function and the decay function. So the base form, the parent function for a exponential function is y equals a to the power of x, where x is your exponent, variable is an exponent, and a is some integer. And it doesn't necessarily have to be an integer; it can be any value, but the equations we're going to be working with in terms of graphs will most commonly be an integer value. But let's look at a very base version. Let's look at 2 to the power of x. So y equals 2 to the power of x, and we can create a set of points for this. So let's set up a table of values. We have x, we have -2, -1, 0, 1, and 2. So for -2 for x, that's 2 to the power of -2. That's would be, let's put it here, 2 to the power of -2. It's not negative, it's just negative exponent, so this becomes 1 over 2 squared, which is 1 over 4. So 1/4 or 0.25 is our first value. 2 to the power of -1, that's 0.5. 2 to the power of 0 is 1. We know the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. So if we plot these points, we have -2, 0.5, -1, 0.5, 0, 1, 1, 2, and 1, 4. We can already see this curve is hugging the x-axis here, and all of a sudden just shoots up and starts to skyrocket. That is our growth function. It starts very low and gets very large very, very quick. The decay function is similar to growth. It's just a horizontal reflection, so it would be y equals 2 to the power of -x. It would be the same values but reflected. So we still have 0, 1, and then we have -1, 2, -2, 4, 1, 0.5, and 1, 0.25. And again, we can see the curve hugging the x-axis, going backwards, but easier for me to draw it this way, as it shoots up. So in this case, it's coming from some very large values and drops very, very quick and approaches 0 very, very, very quick. So we have the growth function and the decay function, and we can really see how it grows very, very quick and how it decays very, very quick. Now, for the exponential function, you can't equal 0. This in no way is going to equal 0 because there is no exponents. There's no value to the power of an exponent is going to give us a value 0. It's impossible. So our function actually can't touch the x-axis here. Unless we transform. So these graphs can be transformed the same way we've seen with other transform functions of the form a and f of k times x minus t plus c. Our focus is creating functions for real situations. So our general formula is going to look a bit different. Our general formula here is f of x equals a 1 plus or minus r to the power of kx plus c. So this function here, a and c represent different values. In this case, A is the initial amount, the original amount of something that you start with. The plus or minus, that depends on what function you're working with. If we are adding, then it's growth. Subtracting, it is decay. So this, again, is our growth, and this is our decay. R is the rate where something changes in these scenarios. C is essentially kind of like the asymptote, what value your function, your scenario is restricted by. Maybe we can't drop below a certain value, so that would be our asymptote defining that. Again, your asymptote here is your x-axis. And then K, well, K is industry's value. This is kind of the value that, let's say we have your rate, and your rate changes by a certain time. Usually we look at it in years. Sometimes it could be you're given that, oh, the rate changes every minute. So you have to pay attention to that. And then once you have your base rate, maybe something happens faster, maybe something doesn't happen as often. So K is often a fraction. And essentially, it will show how long it takes for your rate, growth or decay, to occur. And we can see an example of this down below. In this example here, we want to write the equation that models the scenario. It says a particular banking investment grows at a rate of 5% every 2 years. Originally, there's $1,000 invested. I'm going to write an equation for the amount of money A in investment in years, after T years. So we do have some values here. We have the original amount, that's 1,000. This is our A value. We have a rate, that's our R. And then it says here, every 2 years. So this is going to be our K value. Let's see what we're going to do with that in a minute. So let's set this up. So we have a total amount. So it says the amount of money A. So A is equal to our original amount, 1,000, multiplying 1 plus. Now, is this minus or plus? Well, it's growth. It's growth. So it's plus, and we have a rate. Now, we don't say 5. We don't say 5%. We don't say 5%. We need the 5% as its decimal value. So that would be 0.05. And then this is the R of X, or in this case, T. But we have that K value here. So what happens with K here? Well, it says every 2 years. So this is where you have to think about this a little bit different here. So normally you'd say, okay, this growth rate would normally be every year. If it's every 2 years, then that must mean that it's happening half as long, or it's taking twice as long to get there. So let's actually think of that in sense. Twice as long. It takes twice as long for this investment to grow. For investments, usually it's 1 year, so we need to know the context of these questions and how to apply the K value. So it takes twice as long to do this. So if it takes twice as long, that means you'd be stretching the amount horizontally by 2. So if I'm stretching this horizontally by 2, then we need a horizontal stretch. And remember that a fraction for horizontal transformation is a stretch. So K in this case is 1/2. It's not 2. If it was 2, that'd be a compressor. It means maybe it happens every 6 months. So this is our equation that models this scenario. Now, let's say there was a certain amount that they could not go beyond, then that would be your C value here. You'd have an asymptote for this. But let's look at an example where we actually have to solve for X and solve for Y. So a new car costs $48,000. It loses 16% of its value each year after it is purchased. This is called depreciation. And you own the car before its value is below 10,000. Before we can even do that, we need an equation here. We need to set up an equation to solve for, well, the y and x as independent dependents here. So we have value and time. So our value is equal to the initial amount, 48,000, times 1. This is it's a losing value, so this is decay. So it's minus this rate, 0.16, and then it's each year, so it's just the power of t, so t is number of years, and we have our equation here. So let's actually simplify this. That's equal to 48,000 times 0.84 power of t, so subtract that 1 minus 0.16. So this is our equation. Okay, let's do A. So A states we want the value of the automobile after 48 months. So 48 months, this is in years, so 48 months is equal to 48 divided by 12. That gives us 4 years. So t equals 4. So we're going to substitute 4 into our equation here. So that gives us v equals 48,000 times 0.84 to the power of 4. And you can plug this in your calculator and you get 23,893. So that'll be how much our car is worth after 4 years. It's a big drop, actually. Okay, now let's work with B here. So B has a trick in it that we have to be aware of, something we haven't done before. So in B, we want to know when a car is in B 10,000. So that's when V, that's V. So that means that 10,000 is equal to 40,000 times 0.84 here. We need to solve for t. Now here's the problem. T is in the exponent. There's no, we don't really have the methods yet to solve for that. So we are going to solve for it, and there's to be a trick that we're going to use that you're going to have to kind of work with using a calculator here. If you have your variable in the exponent, you need to get that bracket that it's above alone. So I need to divide both sides by 48,000 here. Cancel. I'm left with 0.20833 roughly equal to 0.84 to the power of t. Now I can still keep the brackets. Don't need the brackets there, but I'll keep the brackets. So what's happening here is on your calculator you're going to look for this button. You're going to look for log, and maybe it's log little square, or maybe it's log x, or maybe 10x, or log y. But probably you're just going to find log itself. Now, what log is it's an inverse of the exponential function, and it allows us to solve for the variable if it's in the exponent. So what we need to do is you're going to do the log of your constant, so 0.20833. divided by the log of your base, the base of the exponent. So that's 0.4, and that's equal to your exponent, in this case t. So doing log of 0.20833 over log of 0.4, that's going to give us 8.997 equal to t. That's pretty much 9 years. So it takes 9 years for our car to reach a value of or below 10,000. Now, if you have trouble getting this value, putting this in your calculator, please let me know so we can go over that. Depending on your calculator, you can literally just do log of this divided by log of that. Maybe you have to do 0.20833, and then you press log, and then you do divide, then you do 0.84, and then you press log. It depends on your calculator. I don't know what calculator you have, so you just need to test it out and see what